is Sao Mai. I'm a researcher at NSTA at UBS, and I'm also affiliated with the Flowers team of India. Today I will present my habilitation titled The Intrinsic Motivation of Reinforcement Learning and Imitation Learning for Sequential Tasks. And we're going to go through body movement analysis, activity of daily living analysis, and intrinsically motivated robots for hierarchical reinforcement. So throughout these years, the outlook on robotics and machine learning has changed a lot. We had robots that can be used in factories, usually. But if you ask currently people, is that your dream when you say robots? They say no, that's not really what we meant by clever robots. Since then, there have been advances in machine learning. For instance, this AlphaGo, who beats the champion of Go. But still, if you ask people, is that the image you have of advanced AI, they would say, no, actually what we want is something that would do cooking for us. But currently, even, we don't have that at our homes. And this can sound very surprising, but it's nothing new. Even Moralek from 1988 said, yeah, actually it's comparatively easy to make computers exhibit adult-level performance, like playing chess. But it's difficult or impossible to give them the skills of 1-year-old when it comes to perception and mobility, of physical interaction, and of moving in our world, which is an open world. So I'd like to frame the issues as a problem of open-ended learning with developmental robots. What I mean by open-ended learning is that we, humans, live in a world where the environment is unbounded, so we don't live only in a room and we explore the room all day. And we have a non-finite number of tasks that we learn and we grow by learning these tasks. And also, we don't have predefined, specified list of tasks, but we learn multitask that is not known in advance, including tasks that can be interrelated, where easy tasks can be composed into more complex tasks. This poses a lot of issues. One of them is that we have to learn a mapping between state, action, and task spaces that can be unbounded in time, space, and complexity. And thus, if we take it naively, we can use infinite dimensionality spaces to use for these mappings, which is impossible to learn. Also, the mappings can be stochastic. It means that when we repeat the same actions, maybe it doesn't repeat in terms of effects, and it can be redundant, which means that there are several ways of carrying the same outcome, the same goal. Mathematically, we can frame that as the learning between an action space, so which movements can I do, and which outcome, so which kind of observable can I have to observe as an effect of my actions. And if we look at cognitive science, they say that we can learn by interacting with our environment, and this is framed as the theory of enactivism, where the theory hypothesizes that cognition is based on situated, embodied agents, and organisms and human mind organize themselves by interacting with the environment. In terms of machine learning, this idea somehow has been translated into reinforcement learning, where we hypothesize that there's the reward hypothesis, that everything that we can learn can be translated into a reward signal, and this is all the information that we need to learn. Within reinforcement learning, there are heuristics for exploring the environment, for collecting data. One of them is called intrinsic motivation. Intrinsic motivation is a theory developed first by psychologists to explain how we are curious, how we use hobbies, spend time and money on activities where we don't learn, we don't earn any direct reward from the outside. On the contrary, we spend time on it because we have some kind of internal reward that is linked to our internal state. Since then, these have been developed into computational models for learning, especially for robots. In terms of learning, we can learn by ourselves, by interacting by ourselves with the environment, but we can also learn through social interaction. So this is the other branch of theory is called social learning theory, where it hypothesizes that the learning benefits from the observation of behavior from another, but also the observation of rewards and punishments. So there are several ways to observe, where we can observe the action of the teacher and try to copy it. And maybe when we try to copy the same action, actually the outcome, the effect can be different. Or we can observe action and the outcome of the teacher, and we use our own actions to replicate the observed effect. There's a connection issue? Okay. And so this idea of social learning has been translated, especially in robotics, through the terms of imitation learning or learning from demonstration. Both have their advantages and disadvantages. So this is faces a lot of issues in terms of exploration and exploration in high dimensionality, especially for multitask learning, whereas imitation learning highly depends on the quality of the demonstrations and the examples that we can observe. And it can be very limited because of that dependency. So in this thesis, I'd like to try to propose a way to merge both of these approaches to tackle open-ended learning, so trying to see how we can deal with complex actions like cooking. So let's see first how we can describe these actions, complex actions. We'll see through activities like cooking, but also other activities like activities of daily living, in context of signals like in smart homes, and we'll see how language models can help model these complex actions. So activities of daily living are cooking, as I said, but also sleeping, bathing, and eating. And what you can see here is a smart home with the fisheye camera, who sees a smart home with somebody living inside. And it can be equipped with cameras, but also with IoTs, so things like presence detector, door opening, temperature, energy consumption sensors. And here we could replicate through our capture of the environment a digital twin that can replicate the activity there. The idea of this is that through these sensors we can observe, we can understand what the human is doing, and then be able to provide automated services. So the first step is to be able to recognize what the person is doing. And for that we use, in this project, a hierarchical activity recognition. So using a camera, a video sequence, we try to label, to recognize what is the person doing, maybe cooking or sleeping, for instance. In this architecture, we use LSTM on 2 layers to be able to recognize that activity. And what we showed is that if we have only 1 layer of LSTM on the top only, then we have this confusion matrix, which shows how well we can recognize, how well we get confused with other labels. Whereas if we use 2 layers of LSTM, like in this shown here, then the performance is much better. So the first conclusion that we got from this result is that complex actions have a hierarchical structure. In this slide, we use cameras which have a lot of information. So from one image, you can already deduce where the person is, but what kind of thing he's doing. Whereas in smart homes, people don't want to be watched by cameras. It's too much intrusive for them. So they would rather have low-quality sensors like IoTs. So as I said, presence detectors, door opening detectors. And what we get from them is not images, but a stream of data, which is here. So we have, for each line, the timestamp, the name of the sensor, and the signal, if it's on or off. And if you say that there's a signal on the kitchen that is on, then you can't say for sure if the person is doing his dishwashing or cooking, or even just going through to get a glass of water. So from one signal, it's very confusing, and it's much less informative than one image. So the challenge here is that we have very non-informative signals. And also the second challenge is that the stream is event-triggered, so we have an irregular and sparse time series compared to cameras. And for activities of daily living, we have a long-range dependency. So what we're doing at this second to be able to recognize depends on what happened 1 minute ago, but also maybe, well, 8 hours ago for big sleepers. And there's also a diversity in the execution of the same activity. If you're a student living in a small flat, you don't have the same stream of data than if you're in a family of 10 people. Right? So the idea is, how can we contextualize each signal of that and take into account the history? For that, we looked into a model that takes into account context, which is languages. So we put into the input of our neural network all the data that we get from the stream, so the sensor signal and the timestamp. And we try to see if we can use an embedding using language models. So we tested 3 language models. One is the transformer decoder that is used in the architecture of GPT. The other is Elmo and word-to-vec. So what is shown here is the architecture using transformer decoder. And on the top of that, we use a classification with 2 layers of LSTM. So on the top, we use the same idea as before with 2 layers of LSTM. And what we showed is that the embeddings that is learned before classification, just using the language model, is very different. So in word-to-vec embedding, here we have the clustering of each signal, depending the color corresponds to each of the labels. And you can see also already clusters. So in the embedding, we can also already see that it's clustered quite well. But in Elmo and GPT, you can see that the clusters are much more smaller. So the difference between the different activities is much more recognized. In terms of results, we have classification using F1 scores on a dataset called CASAS, Carol. And we can see that our embeddings using Elmo and GPT are performing much better than using only the 2 LSTMs without the embedding, or even much better than if you use SCN. So, sorry, it's a convolutional neural network. And if you we use a hierarchical architecture where we have this idea of hierarchy of activities, then the recognition level is much better. So the lesson learned from that is that long-term context is essential to understanding human activity, and actions have a semantic and grammar-like language. And complex actions have a hierarchical structure. This kind of research can be also combined with robotics, as I said, where we use here in the smartphone sensors, and sensors can have some issues recognizing if somebody fell down. So for instance, in this case, the person just kneeled down, but the sensor thought he fell. So when the smartphone is connected to a robot, then the robot can come and interact with the person. And for instance, here the robot is coming to search the person and ask if the person is okay. So
Infection ends. Are you all right?
Yes.
So in this case, the person is okay, and so the robot can resume his activities.
Going back.
Whereas if the person is not okay, then the robot can then trigger a signal to tell the people, the contacts of the person, that something is not fine, and also secure the house. So the robot is connected to the house, so he can like turn off the oven and the kitchen, but also open the doors for access for rescue, so that the rescue doesn't need to spend hours and hours to open the door.
Leak detection ends. Are you all right?
No.
Don't worry. I turned the lights on.
So he turns the lights on to feel secure for the person. And so he sends an email for contact, and by pressing the link, then the person can see what the robot is seeing, and we can imagine you can also take control of the robot to help the person. So now that we've seen that actually tasks that we want robots to do for us, our dream robots, are actually hierarchical tasks, compositional tasks, how can robots actually learn them? How can we do hierarchical learning? So in this project, we had postulated that we should learn tasks, and each task can correspond to a neural network to be created on the go as we discover that these tasks are doable. For instance, this wheeled robot can learn to move around, and it can learn that it can push objects. So these correspond to two neural networks that can be created, and the second one should be only created once the robot knows that there are green objects around. So this translates the idea of emergence of the concept of each task. So tasks are created online, and can we learn which are the controllables that we have from the observations of our environment. And once we know what we should learn to control, then what are the inputs, what are the dependencies of that task. And for that we use prediction error to be able to select these inputs. So the faint idea behind it is tool use. So how the outputs of learned tasks can become the inputs of other tasks. So if we control how to the position of a green object, how can this green object be used to push another object and so become a tool? Here, the idea behind it is translated through the fact that we will use an action space that grows. So as along with the controllables that we can master, we then add them as possible actions that can be used for other tasks. So this research translates the idea of affordance. So we use object properties and continuous sensory motor space. Here we have a mobile robot that moves in a room where there are red objects that are obstacles that are not movable, and green objects that are movable objects. And the robot has access to inputs like the LiDAR, the properties, colors of the objects, and it can actionate its wheels. And the question is, which model can translate the fact that you can control the tool use of an object, so pushing an object with another. So generally, in machine learning, we say that, well, the robot should decompose into a subtask, which is controlling its own position, and then we only learn the parameters of model A and model B. Here, what we say is that we don't even know that there's this subtask, and the robot has to discover by itself. So this learning is between a primitive action, which is a 2D, but also a state space, which is 124D. And by using intrinsic motivation to create these models, so the robot learns first to control its position in function of the wheel command and the LiDAR, which is the distance to obstacles. And we can see the task evaluation through time of that. So it learns quite early this task. And it recruits these inputs as inputs for its controllable. And later on, once it knows how to control its position, then it learns how to control an object A position. And it recruits the inputs, which are the relative position and also the size of the object, which will change how it moves when it is pushed. And this second task, you can see the green curve is learned a bit later. And so we can see that automatically it learns a curriculum where it learns the easy task first and then the more difficult task second. And later on, it can use it for any object, object A and object B, and use that to be able to push an object with the other. So the third task here is learned even later. The result here shows that through this mechanism, we can learn multiple tasks, and we learn from using curriculum learning. So simple tasks first and composing them for more complex tasks. And it builds this hierarchy between tasks using intrinsic motivation. The limitations of this is that even though the models are small, because we use small neural networks, the input space is still very large because they are continuous spaces, and learning in continuous spaces means that we have to deal with exploration in a large environment. So my second postulate is that maybe we can try to reduce the dimensionality of that space by discretizing the environment. So even if the environment in itself is continuous, so here we have an ant robot that is moving in a maze. So the environment is completely continuous and the commands of the legs are continuous. But here, if I show it to you, you already have a discretization of the space by saying there's a space down there on the bottom, and there's a space here where you have to go and look at the camera to have security check before the door opens. And then you have another space near the goal where you have to go to the left. So this discretization seems very natural for us, but less natural for robots. So this discretization goes in with the idea that to learn hard tasks, we can select simple learning goals to decompose a task. And here the goal representation is crucial in hierarchical reinforcement learning. And a good goal representation is to preserve an environment's dynamics and use that representation to learn then politics. So the question here is, how can we efficiently learn a goal representation for hierarchical reinforcement learning that captures complex environment dynamics? What are the good properties? So if the goal space is equal to the sensor space, so continuous, then goals are too granular and we spend too much time exploring. So we need a spatial abstraction which is discrete. In classical hierarchical reinforcement learning, the goal space is equal to the state space. So for instance, in this maze, the learner would select points in the space as sub-goals, and then we drive the robot, and then we select the next goal, etc. Whereas in our spatial abstraction, what we do is that we discretize the environment into two, for instance here, into two regions, and then we select goals which are regions themselves. And we will update the representation of these regions by splitting, for instance, this region here into these two regions into three that we can see here. And this split is based on reachability analysis by looking at the trajectories that are explored. And from that, we have the optimal high-level trajectory, which would be G0 second, then G0 prime, then G1 to reach the exit. So now that we've seen different representations of hierarchical actions, I'd like to expand more on how we can use that for learning, not only by self-exploration, by reinforcement learning, but by combining it with social guidance, with active learning. So the idea here is to see how we can learn hierarchical tasks with active imitation learning. So to come back to the idea of intrinsic motivation explains how this lady here chooses this ball to play with, whereas all the other toys around are very interesting too. And actually, so psychologists say that they select tasks or objects to learn that are going to fit their developmental process. So this ball is fine for young children, whereas older people like us would be quickly bored by a ball and we would like more complex tasks to deal with. And this goes well with the idea of self-exploration, but actually how can it be extended for social learning? When we are babies, we also interact with other people and we can learn from them. So sometimes actually children just ignore adults who want to play with them, but sometimes they're very happy to play with them. And sometimes there are several people who play with them. So how do they select whom to play with? So we want to extend the idea of intrinsic motivation with teachers. So how do we select teachers using intrinsic motivation? How can we frame the intrinsic motivation in reinforcement learning framework? And what is the reward function or the reward in the reward hypothesis to interact with teachers? So in this experiment, here we have a robot who wants to party, and he's in front of a DJ table, and he can push the buttons around, the blue and green buttons, and to make music. So he can emit sounds, that burst sounds, or more sustainable sounds. So here we have multitask learning, so which model can induce the hand position, the place of buttons, and the music, and which are the control models of the arm. So we have to learn a mapping between a task space and an action space, where the task space is a composite task space of observables, so observables of different nature, positions and sounds. And the action space here, we don't know how complex actions are, so we don't know if we need 1 second or 5 minutes to finish our music. So the action space is a succession of actions, but a priori it's a non-finite succession of actions. We want to learn the relationship between tasks, so this decomposition of task is not given in advance to the robot, it has to learn it through this hierarchical learning, that to move the blue object to a place, it first goes to the initial position of the blue object and move it to the end position, etc. for the green object, and to move both objects or to emit music, it needs to move both, etc. So to learn, it can learn again by exploring by himself. So he can learn which actions move the blue object and which actions move the green object. But he can also observe from the teacher that to make longer music, he can make a sound and then do something else, like touch another place on the table. And so here, the teacher can show just a task decomposition, but he can also show how to, which command will be able to touch the table at that place. And combining both knowledges, so that he already knows how to make a sound, then he can combine into a longer sequence of actions and then deal with more and more complex tasks. Here, the idea is that we deal with multitask learning, or where we have policies of different complexities, where it needs to be learned by sequences of primitive actions of adapted size, and we use a task-oriented representation of compound actions. We again have the idea of hierarchical and recursive task decomposition. For task decomposition, in this research, we propose a representation which is again goal-oriented, where the goal is represented by an effect. Here is going to be the positions x, y of both objects, and it will be decomposed into two sub-goals. So here is going to be the position of the blue object, and here the position of the green object. And we are going to learn through automatic curriculum learning. The result shows that we can learn very simple tasks like reaching a point. And using our algorithm, which is called socially guided intrinsic motivation with procedure babbling, it can also learn more complex tasks. So here it's decompose it into 4 subtasks, which is reaching the blue object, placing it to the new position, then reaching the green object, moving it to the second position, and with that it makes a burst sound. Sorry, I don't know why it makes a sound. And then it makes another point, another movement to make a more complex sound. Whereas if we don't have this representation of procedure, then the robot still can do simple tasks, but when we ask it to make a more complex task, like emitting a sound, you will see that the movement has nothing to do. It doesn't even start with the first steps because it doesn't have this knowledge or representation of task decomposition. So here we show the results. So the x-axis is the time of learning, the process of learning, and each color corresponds to which task it spends most time on. And we can see that it starts first with easy task, omega 0, and ends in the end with the yellow, which is omega 5, so the more complex task. So our algorithm chooses the simple task first, complex task in the end. And how does it learn? Well, also by using demonstrations from teachers. Here we have several teachers, and we can see that in the beginning it uses mostly the imitation learning from teachers, whereas in the end we see that it uses more autonomous learning, so the yellow, which is autonomous learning. So SGM relies on teachers in the beginning and learns more autonomously in the end. As per results, we also show here the histogram of what are the strategies, which teachers he uses for which task. So for simple tasks, which is omega 0, so the highest is autonomous action, so it uses mostly autonomous exploration to learn more simple tasks. Whereas for the most complex task, which is omega 5, we can see here that it spends most of its time on this because it's the most complex task, whereas it spends less time on the simple tasks. For tasks with teachers, so from omega 0 to omega 3, it has different teachers that can help him learn. And we can see that every time, for instance, omega 2, it chooses the right teacher, which is the teacher for the task, who is expert in the task. So somehow the learner can do autonomous exploration of the task for simple tasks. But for complex tasks, he will try to explore task decomposition, but also ask teachers and identify who is the expert in which task to be able to solicit his help. We want to expand this idea by saying that yes, we have a robot that can devise his own curriculum and strategy for learning. So which task to learn first, which order, and also which teacher to solicit and how to learn directly the task or by decomposing the task. And how can we turn it back into saying, instead of having a robot learn, how can the robot teach somebody to learn once it has this representation? So this is the idea of intelligent tutoring systems. So the idea is to have a recommendation system to choose exercises for human learners. And ITS should propose exercises that are not too easy, not too difficult. And actually this translates again the ideas that I've developed so far, which is based on intrinsic motivation and learning with teachers using zone of proximal development. So zone of proximal development is the idea that we have a dynamic set of activities that maximize the learning progress. And it translates well with the idea of intrinsic motivation or articulatory curiosity, where we want to maximize the learning progress for the learner. And so far we've used it for robot learners, but here we can use it for human learners. And as I explained how these models are being used for robots. Here the idea is that we can have a set of exercises, and each exercise will train a different skill, and the skills can be related to each other. So if we want to learn multiplication, for instance, we should learn first how to do addition, and for each of those skills there are different exercises. If we have this representation of exercises and skills, then we can choose exercises by zone of proximal development based on knowledge structure. And the ZPD will add new exercises when the knowledge components are unlocked, and it will remove exercises when the knowledge components become too easy. So to start with, we will propose exercises that correspond to knowledge components that don't have any prerequisites. For instance, addition here, we can propose all the exercises corresponding to this, whereas multiplication, the exercise corresponding are not proposed yet. And once the learner makes progress, here he masters well exercise 1. So validating exercise 1 means that this knowledge component, addition, is well mastered. And then we say, okay, we can move to the next step. We can add multiplication and the exercises corresponding. But now that we are all geniuses in math, if people give us exercise and addition, it will be very boring. So when the skill is really well mastered, then we should take out the easy exercises. So exercise 1 should be taken out of the zone of proximal development. So this way, the set of exercises recommended to the learner is dynamically updated. This idea should be applied for robot coaches. For instance, this project of robot coach for physical rehabilitation. So this is a project that I led when I was at l'IMT in conjunction, in collaboration with Sergi Lepest and Génération Robot, where we use the open source robot, humanoid robot, Koki, as a rehabilitation robot coach. So it's open source, so we could change all the software and the hardware. So we can see the red parts are the parts that we have changed in terms of hardware.
Raise the left arm, stretch, while inhaling. Slowly bend to the right while exhaling to stretch the left flank. Straighten by inhaling, then lower the arm while exhaling.
So the robot can give instructions to the patient.
Raise the right arm, stretch, while inhaling.
Both oral and visual. And in this experiment, we only use one Kinect, a single camera, to analyze the pose, human pose of the patient and give him feedback. So here the patient is very straight.
The workout exercise could be done better. Try to lean a little bit more to the left side. It's your turn.
And on this second attempt, the patient is more leaning to the side. He's no longer having his back straight, and so he's going to have a better feedback.
The workout exercise has been properly done.
So in this project, we carry out the clinical experiments using double-blind clinical trials during 2 years with 31 patients aged from 18 to 70 years old. They were exercising 30 minutes per day, so that's a long-term interaction. From that, we also were able to assess usability and acceptability, and we collected a medical data set of patients carrying out medical exercises. And we also proposed an economical model of a robot through our collaboration with health economists.